Hello friends of Sudoku, this is a hard Sudoku from sudokuexchange.com. Let's see what we can do with this grid here. We have a 6 blocking over, another 6 blocking over, and this 6 blocks up, so a 6 must go here. A 7 blocks over here, a 7 blocks over here, so here's a 7. A 3 blocks over like so, and this 3 also blocks over while this 3 blocks up, so here's a 3. 3 blocks down, 3 blocks over, 3 blocks up, 3 goes here. 3 blocks over and up and down, and this is therefore also a 3. There's an 8 blocking over here and another 8 blocking over here and an 8 blocking up, so an 8 must go here. 8 blocking up and over, so here's another 8. We know that this 2 blocks here and this 2 blocks here, so a 2 must go here in the first row. These now must be a 4 and a 9. Let's see, a 9 blocks over here. Can we do more with that? No, not really. We only have one 4 in the grid. 4s will be a little difficult here in the beginning. But we can do something with the 3s. A couple of 3s block down and a couple of 3s block over. So here's a 3. A 2, 4, and an 8 for these squares here. Can we do anything with that? Yes, we can, because we have a 2 and an 8 blocking here. So here's a 4. And a 2 blocks here. So this is an 8, and therefore this must be the 2. Now we got an 8 blocking down, another 8 blocking across, and one more blocking across. So an 8 goes here. 1, 5, and a 6 for these squares here. And oh, well, hang on, a 6 blocks over and over, so here's a 6. Therefore, one of these must be a 6, and this must be a 1 or a 5. And one of these must be a 5, because we have a 5 blocking over, and therefore one of these must be a 5. But we can do something over here with the 5s, can't we? Because the 5 blocks over here, and this blocks over, and this blocks down, so a 5 must go here. Now we just need 1, 4, and a 2 for these squares. And we only have a single one in the grid so far, so that's also going to be a little troublesome. So let's instead look at these squares. They must be a 1 and a 4. This 4 blocks over, so a 4 goes over here somewhere. Nah, that is not enough. Not enough information. We need a 9 for the second column. The 9 blocks here, the 9 blocks here, and these 2 9s block here and here. So a 9 must go here. For column 7, we need a 1, 2, 5, and a 6. We got a 5 and a 6 here, so this is a 1 or a 2. We got a 5 and a 6 here, so this is also a 1 or a 2. So these two squares, therefore, must be a 5 and a 6 pair. And does that mean anything in terms of the 5s maybe, or the 6s? The 6, 5 or a 6. I'm still looking for a 6 for one of these squares here, and it must be this or this. But we also have potential 6s here. So it's not really giving me anything except it's making it more clear that these squares must be a 1, 2, and a 7. We know that 7 must go here or here. So this is a 1 or a 2. But we kind of knew that already, didn't we? Because this is a 4, and we need a 1, 2, and a 4 for the column. So many roads lead to Rome, I think is the saying. And for this Sudoku, it certainly seems to be true. But the restriction here of a 5 and a 6 lets me look at the 2 and the 4. We still need a 2 and a 4 for the row, and the 2 and the 4 are blocked from going here. Therefore, 2 and a 4 must go here, mustn't they? So 2, 4. So this is a 1, 5, and a 6. And we know that this cannot be a 6, so this must be a 1 or a 5. But there is some fruit that is even more low-hanging, and that is a 2. Let me repeat. This is a 5, 6, therefore it cannot be a 2. A 2 blocks here, so none of these can be a 2. Now, in theory, both of these could be 2s if it weren't for the fact that this 2 blocks down, this 2 blocks over, and one of these must be a 2. Therefore, this cannot be a 2. Therefore, it must be a 4, and this must be a 2. And here I'm kind of not getting on with the puzzle. Let's see, a 9 here and a 9 here. No, I don't know how to proceed with this puzzle. So for this puzzle, again, I'm going to input pencil marks. And again, I'm going to forego the Snyder notation. If you don't know Snyder notation stipulates that if a digit can go as a candidate in a 3x3 box exactly twice, then we can enter it. So let's see if I can find an example. Let me try these 3 squares. They must be a 1, 4, or a 7. The 7 blocks down here. So in theory, we could enter a 7 here and a 7 here. And we can probably find some other examples. Yes, we can find these 2. They can also be 7s. So back to these squares, they could be a 4, 5, and a 9. The 5 blocks over here. So one of these could be a 5. And therefore, one of these must be a 5 as well. We got a 5 blocking up here and a 5 blocking down here. So one of these can be a 5. So this is a Snyder notation. The idea being that if you haven't filled in a whole lot of digits already, then Snyder notation will help you by creating a better overview over what is still missing. And if there are some other digits that can only go here and thus forming, for example, a pair. In my experience, however, if we do this in a puzzle of a certain complexity where we have already done everything we could to find singles, then Snyder notation is probably not going to be very helpful in letting us find further digits. So what I do is I bypass the entire Snyder notation and instead I look for by-value cells. By-value cells are cells that can take exactly 2 values, and it doesn't matter where in the grid they appear. This kind of notation often helps me find chains, X-wings, finned X-wings, skyscrapers, and the like. So I will pause the video for a second while I input all the by-value cells candidates that I can find. So hang on for just a split second. So I'm back and I have now entered values into all the squares that can take exactly 2 candidates. It doesn't look like much, but quite often this is a huge help without cluttering the grid with a lot of superfluous digits. Let's look at the 4s, for example, and I think that we can isolate 4s now. But it takes a little bit of imagination and the knowledge of chains. In this case, I think it's called a colored change. The colored change works like this. Let's say this is a 4. The next link in the chain must be here, because if this is a 4, this cannot be a 4. And since this 4 blocks up here, we know that this must be a 4. If this is a 4, then this cannot be a 4, and this must be a 4. This square is, let's say it's a blue, green, blue, green, blue, green, blue. So this square is blue, and this is green. So the rule of a colored chain is that any square that can see a blue and a green square cannot contain the number that we are looking for. In this case, it's a 4. So this square cannot be a 4. So let's go through this again. If this is a 4, we don't even have to look at what if this is a 9. We just have to look at if this is a 4, then this cannot be a 4. And therefore this must be a 4. Therefore this cannot, but this must be a 4. This cannot be a 4, and this must be a 4. So it doesn't really matter if this is a 4 or not. What matters is that this is blue, green, blue, green, blue, green, blue. We have a green here and a blue here, so this square cannot be a 4. And that has a certain ramification, because now we know that a 4 must go in one of these two squares. And that means that this square must be a 1 or a 7, and we can input those. The next is more difficult, at least for me, because I rarely spot them, and I had to look a long time at this puzzle to find it. I think it's called a V or a W wing, and it involves the 1s and the 2s in this chute here. But the logic really is quite simple. I know we haven't input any values here, but let's just, for the sake of argument, input the 1, 2, and the 4 here, even though I don't like to input values in cells that can take more than 2 values. But let's just do it for this isolated instance. If this is a 1, then this is a 4. I think we can agree on that. If this is not a 1, then it must be a 2. And if it is a 2, then this is a 1, this is a 4, this is a 1, this is a 2, and this must be a 4. So it doesn't really matter the values of these. This can only be a 4. So we can input a 4 here. This 4 blocks over, so this is a 4, and this must therefore be a 9. This 4 blocks up, and therefore this is a 4. Now these are a 1 and a 5. We do have a 5 in one of these two squares, though, and therefore this cannot be a 5. It must be a 1, and the 5 must go here. Here we are looking for a 9 and a 5. We got a 9 blocking up, so a 5 goes here and a 9 here. 5 blocks down and up, therefore a 5 goes here, and now I think, yes, here's a 5 for column 4. And that gives us a 5 for this square. Here we're looking across for a 1 and a 6. We got a 6 blocking up, so this is a 1 and this is a 6. The only square left here now is a 6, making this square 6 as well. And now this square cannot be a 1, so the 1 must go here, and this must be a 7. We still have our 1 and a 2 here, 1 and a 2 here, but here now we have 1s and 2s. Remember how these work by value cells, so we can take it at face value that this square must be a 2 and this must be a 1. Therefore, this is a 1 and this must be a 2. This square didn't have any candidates, but it can only be a 7. And this can only be a 4, while this only can be a 1. A 2 must go here, and a 1 here. A 1 blocks over and a 1 blocks down, so a 1 goes here. This must be a 7, and this must be a 4, which blocks over, making this a 4. And now we just need to find a 9, 7, and a 2. Let's see, there's 2 blocking over here, so this is a 2. 7 blocks down here, so this is a 9, and this is a 7. This was a rather long-winded video, but I thought it was necessary to explain the color chain and also the W wing, because they do appear quite often in more difficult puzzles than the ones that I usually present on the channel. I hope that you found it useful and that you will come back for more. Bye for now.